Hello all, welcome to my tutorial on velocity by instant center method. As we all know, it's a graphical method where we are using to find out the velocity, linear velocity, angular velocity of mechanisms. For any planar moving links, you can select the instant center related to another link by just seeing this diagram. For a turning pair, it will be the hinged point. The instant center will be the hinged point. Usually these are permanent instant centers. Then for a rolling pair, the point of contact will be the instant center. Then for a pure sliding or a translation motion, you can assume the instant center is at infinity, and for surfaces like concave and convex, the radius of curvature of the sliding surface is actually the instant center. So these is basically used to locate all the fixed and permanent instant centers in a mechanism, but we have neither fixed nor permanent instant centers also. For that we are using the Kennedy's theorem, Arnold's Kennedy's theorem to locate those instant centers. As we know, Arnold's Kennedy's theorem states that if you have three links move related to each other, it should have definitely three instant centers, and all these instant centers should lie on a same line. We'll see how to do a problem here. The first thing, we want to find out the total number of instant centers in a given mechanism. For that you can use the formula n is equal to n minus 1 by 2. In this particular mechanism you can see 6 linkages are there. Okay, so 6 link means n, small n is 6, and from there we can find out the total number of instant center is 6 into 5 divided by 2, that is nothing but 15. For that you can prepare a table diagram also. It will be like this. For in the top row you can write the links, that is 1, 2, 3, 4, 5, 6. These are various links. This is link number 1, fixed link, and the crank is link 2, 3, 4, 5 and 6. So total links you have to write. Then you can write the instant center. So this is the instant centers which are related to the fixed link. Okay, so you can write 1, 2, 1, 3, 1, 4, 1, 5 and 1, 6. Okay. And next is actually 2, 1. 2, 1 is already here, so no need to write. So 2, 3, 2, 4, 2, 5 and 2, 6. Okay. Then coming to 3, you have 3, 1. 3, 1 already came here. 3, 2, 3, 2 already came here. And 3, 4. 3, 4 is here. 3, 5 is here. And 3, 6 is here. Okay. Coming to 4, again you can write like that. 4, 1 is already here. 4, 2 is here. 4, 3 is here. Next is 4, 5 and 4, 6. Okay, and for the fifth link you have 5, 6 only. Okay, so this is a table diagram. We have to prepare, find out, for any problem we have to find out the total number of instant centers. Then we want to name all instant centers. For that we have to draw a table diagram. Okay, then we have to locate all the fixed and permanent instant centers just by analyzing the configuration of the mechanism. If it's as we know, if it's a turning pair, the point of contact, the point of turning, that is a hinge point, will be one instant center. So like that we want to locate physically all the instant centers. Then the remaining instant centers which are not fixed and not permanent, neither fixed nor permanent, we have to use the Arnold's Kennedy's theorem. So this is how a problem we have to do. First you have to find out the total number of instant centers, then you have to make a table diagram to find out the total instant centers and name it then we want to locate it physically in the mechanism. For that you have to draw the mechanism on a scaled or the actual size, whatever, but you have to draw it on the actual dimensions. Okay, then we have to locate it. Then we will find out the neither fixed nor permanent by using Arnold's Kennedy's theorem. Okay, so we will now move to a problem. So this is a problem as shown. In a pin joint 4-bar mechanism as shown in figure, the crank AB is 300 mm, BC is equal to CD is 360 mm, and AD is 600 mm. The angle BAD, that is the crank angle, is 60 degree. The crank AB rotates uniformly at 100 RPM. That is very important. N RPM, N AB is equal to 100 RPM. And locate all the instant centers and find out the angular velocity of link BC and CD also we can find out. Okay, so this is the problem. So now we know all the dimensions. So first we have to prepare the table diagram. For that we want to find out the total number of instant centers. Okay, so the total number of instant centers we can locate by using the formula n is equal to n into n minus 1 by 2, which is equal to 6. Then we will prepare the table diagram like this. The table diagram will be the top row will be the links, that is 1, 2, 3, 4. We have a 4-bar mechanism here. So 1, 2, 3, 4 will be there. Then we will name all the instant centers. So this will be the I12, this is I13, I14, I12, 13 and 14, then 23 and 24 and 34. Okay, so this will be total number of instant centers. Now we are going to graphically construct the mechanism. Okay, so here I am using the FX draw tool to draw the mechanism and locate the instant centers. You can just download, or you can do it in the by using your regular geometrical tools like protractor, scales and compass. Okay, I will just first fix the scale. Okay, so for the scale, what I am taking here is the scale as, then I will draw the mechanism. Okay, so that is 600, so my dimension will be 60. Okay, the straight line will be drawn with the okay, then I'll draw another line which is the crank at an angle 60 degree and the length is nothing but 30. Okay, 60 degree and 30 mm. Okay, so that is the crank. Then I'll go for finding out the point C, that is the connecting point of the coupler and the rocker. So that I'll just take an arc. Okay, and that is 36 mm. Okay, then one more arc. Start from here. Okay, so the meeting point is my C, where I will draw the next line. That is the point of intersection, and also the intersection. Okay, right. So now I finish my mechanism. Now I am going to name it A, B, C, D. Okay, so this is the mechanism A, B, C, D. AD is my fixed link. So now I finish my space diagram. So this is a space diagram. we'll first number the links. Okay. Now we'll find out the fixed and permanent instant centers. So from the table diagram, we know we have 6 instant centers: I1, 2, 1, 3, 1, 4, 2, 3, 2, 4 and 3, 4. Okay, so we're now going to locate all these instant centers. So this is link 1 and 2. So definitely this point will be an instant center. We say it as instant center I12, instant center I23. So that will be I23 because this is 2 and 3. Okay, so between 2 and 3, that is I23. This hinge point is actually between 3 and 4. Okay, 3 and 4. So that is I34. 3, 4, I34, and this hinge point is between I1 and 4. So that will be I14. So now we located all the 4 fixed bar permanent instant centers. We have fixed instant centers and we have the permanent instant centers. Now the remaining 2 more instant centers, that is actually 1, 2 is located, 1, 4 is located, 2, 3 is located and 3, 4 is located as per the diagram. 1, 2, 2, 3, 3, 4 and 1, 4. These instant centers, that is I13 and I24, we yet to determine. Okay, so how we are going to determine that? We are using the Arnold's Kennedy's theorem to locate I13. Okay, the instant center I13. We are using the Arnold's Kennedy's theorem. So for that, Arnold's Kennedy's theorem says that if 3 bodies are moving simultaneously, relatively each other, it has definitely 3 instant centers from the equation n is equal to n minus 1 by 2. So that will be 3. And these 3 instant centers should lie on a same line. Okay, so we will consider these 3 links, that is 1, 2 and 3. We know that 1, 2 is already here we located, then 2, 3 is already located here, that is here I23. What is the remaining one? That is I13. And Arnold's Kennedy's theorem says that it will be lie in line with I23 and I12. Okay, so for that we'll just draw a line from this point and it should be in line with I12 and I23. Okay, so we'll just click. I will draw a line like this. Okay, see. So what Arnold's Kennedy's theorem says that I13 should lie in a line which joins I23 and I12. Okay, so we don't know actually the location, but definitely it should be in this line. Okay. Then we take the other configuration. We take link number 1, 4 and 3. Okay, so 1, 4 and 3 in this direction, so that we can see I34 it is already here, I14 it is already here, the remaining is I13. Okay, so that definitely lies in a line which is connecting I34 and I14. So that is Kennedy's theorem says. So that again we'll draw a line which is in line with I12. Okay, so the meeting point will definitely, this is the meeting point, and that intersection point will be our I13. So this is the I13. Okay, so now we have remaining one more is there, that is I24. Okay, so all the 5 out of the 6 we find out all the 5, we located all the 5. Now the remaining is I2 and 4. For that, what we will choose the link 2, 3 and 4 and 2, 1 and 4. Okay, so the first we will choose 2, 3 and 4. Definitely 3 are moving relative to each other and has 3 instant centers. I23 is already located here. I34 is already located here. The remaining is I24, which should lie in this line. Okay, so we'll draw another line starting from here. We'll extend it. It should be parallel, or it should contain both the points 2 and 3. All right. Now we will take in this direction 2, 1 and 4. So 2, 1, 4 we have I12 which is already here, I14 which is already here. The remaining instant center is I24, which should lie in I12 and I14, same line. Okay, so for that again we'll draw a line starting from here, and it should contain both I12 and okay. So this meeting point will be our what? Our I24. So this intersection point will be I24. That will be I24. Okay. So now we located all the 6 instant centers, and our question is to find out the angular velocities of what? This link and this link. Okay, so we want to find out the angular velocity of this and this. Okay, for that again in the question it is given that the RPM of the crank AB is 100. So from there we will first find out the omega, angular velocity of the crank, by using the formula 2 pi n by 60. Omega AB is equal to 2 pi n by 60, which is equal to 10.46 radians per second. So now we have the angular velocity of the link. If you know the angular velocity of the link, which is rotating clockwise direction, definitely the velocity of the point B we can find out. That is the angular velocity of the link into length of that link. That is omega AB into AB, link length. That is 10.46 radians per second into it is 300 mm. That is 0.3 meters, which is equal to 3.138 meter per second. At the same time, we have another the point B is actually, it is sharing by both link AB and BC. Okay, so it's a point of link B. So if you consider this link, that is the link number 3, if you consider, it is moving rotating about link number 1 about this point. Okay, so how can we find out the angular velocity about this point? If you know this length, the link is rotating about this point. Okay, so we can physically measure that. Okay, so we can physically measure that dimension. Okay, so we'll get it as 500 mm. Okay, so we got that as 500 mm. So scale is 10 mm. So this is actually 50 mm. That means really it will be 500 mm. Okay, so now we got the distance of I13 to IB, so that we can find out the omega of BC. Omega is equal to V B, absolute velocity of B, by the radius of rotation. That is nothing but I13 B. Okay, I13 B is equal to VB already find out 3.138 divided by 0.5, which is nothing but 6.282 radians per second. So that is the angular velocity of the connecting rod. Now we find out the angular velocity of the rocker. So the rocker is CD. Okay, so the rocker is rotating about the point D. So if you know the angular velocity of this link, you can find out the linear velocity of the point C. How can we find out the linear velocity of the point C? So the point C is rotating about I13. Okay, so we will first measure this length. That will be that is 36. Okay, so 36 mm. So when it comes to scale, it is 360 mm, nothing but 0.36 meters. Okay, so we know the angular velocity of BC, so we can find out the linear velocity of C, that is, so the linear velocity VC is nothing but omega BC into I13C can be equal to omega BC. We already know omega BC. We already find that is 6.282 into 0.36, 2.26 meter per second. Okay, so this is the linear velocity of the point C. So now we know the linear velocity of the point C, which is shared by both the coupler as well as the rocker. Okay, so now we know the linear velocity of point C. Now we can find out the angular velocity of the rocker. Rocker is DC. Okay, rocker is this link DC. So how we can find out that a rocker? So omega CD is equal to VC divided by C. So that is the angular velocity of the link, output link, which is equal to 2.26 divided by 0.36, which is equal to 6.83 rads per second. Okay, so that's how we are finding out the angular velocity of the follower also. Okay, so this is how we finding the linear velocities and angular velocity using the instant center method. Hope you all understand this, and we will winding up for today's session. I will come with one more problem in a slider crank mechanics.